Welcome to this second session about MPI, which will be presented by Louant from Liège for the first part about collective communications, and then by Lozanno from ULB for the second part about MPI in Python. The floor is yours, Orion.
Thank you, Damien. So this afternoon, as Damien said, we will talk about collective communication in MPI with C and Fortran. And afterward, we will discuss about the usage of MPI with Python. So far we have covered the topic of point-to-point communication, either using synchronous or asynchronous mode of communication. And this point-to-point communication is just a message that is exchanged between a sender and a receiver, and this sender and receiver, so the source and the destination, is clearly identified. However, in a lot of tasks, a lot of application, you may require collective communication. This collective communication, the idea is you have several types of them. It's first a broadcast, when you send a piece of data to all the processes. A scatter, when you distribute the data between the processes. And then you have the opposite, which is a gather, where you collect data from multiple processes to one process. And then you have the reduction operation, which is collect a lot of data and reduce the size of this data to a smaller size, like, for example, a sum or a product. So the first type of communication, collective communication, is a broadcast. When you have a broadcast, one process that we will call the root process send the data to all the process in a communicator. And for example, in this case, with for process, we have the root process, which is the rank 0, that will send data to all the process in the communicator. So exactly the same piece of data to process with rank 1, 2, and 3. In MPI, this is done using the MPI bcast function, which takes the address of the data you want to broadcast, and then the number of elements in this data, like with the send operation, and the data type of the operation. And this address is also used for receiving the data for the process that they're not the root process. Okay, and then you have this integer which identify the rank of the broadcast. So in our case, previously, the root will be 0, as the piece of data is located in the memory space of the process with rank 0, and will be broadcasted to all the other process in the communicator. So this is the root inside a communicator that is defined using the MPI handle. So as an example, we defined the broadcast root as being the process 0, okay? And in the case of the process that is the broadcast root, we set a value inside a variable, and then we broadcast this value to all the other process. So we do this with the MPI bcast. So we pass the address to the variable we want to broadcast to all the process, and we say that it's one integer, and that the broadcast root is 0 as defined there, and we use the MPI world as usual to describe which communicator we want to use. Okay, and then we print that what the other process have received, and the output of this program. So as we see, we have I am broadcast root with rank 0, and I send value 1, 2, 3, 4, 5. This is exactly as we have defined here in the code. And then we have the broadcast, and at the end of the broadcast, all the process should have the value that the process 0 set. And this is what we see. We see that process 1, 2, and 3 receive the value from the process with rank 0. The idea behind this communication, and I will do this just for the broadcast, but just to give you an idea why use collective communication instead of point-to-point communication for this kind of task. You can do this with a simple point-to-point communication function. So we can do a broadcast with send and receive, but then you will have something similar to what we have done with the example of the sum of integers, is that you will have a loop to all the process that will perform the receive operation, and then you have a loop. You will have a loop on rank 0 with all the send operation to all the process, and then you will have a receive for all process that is different with rank different from 0. Internally, MPI do this differently, and if you do this with simple send and receive, then you have n process minus 1 call to the receive function as well as send. But you can do that in log p being the number of process step by just first sending the value to one of the neighbors. Okay, if we have 8 process, you send to one process, and then this process has the value that is supposed to be broadcasted, and then in the second step, both process with rank 0 and 4 can broadcast the value to process with rank 2 and 6, and then in the third step you can do this for process 6 to 7, 2 to 3, 4 to 5, and 0 to 1. So basically you have 3 steps, okay, and all these steps takes at the same times, occur at the same times. And so the idea is that you have a broadcast that is, of course, the time for the communication multiplied by log 2p, which is the number of time you have to do this step. So it's way more efficient in this implementation than doing this by yourself inside using simple send and receive. So you can have better performance, and you don't need to reinvent the wheel or do the optimization yourself. So as long as a function is available for the task you want to do, it's better to use the collective communication instead of implementing it with simple send and receive. So I will not do this for all the collective communication method that we will see, but it's just to give you an idea why these collective communication function are better than doing it by yourself. And of course, you can represent this another way, which is a tree where each node will then broadcast to 2 other nodes. It works also. The next operation that may be of interest is a scatter. So the elements of an array are distributed in the order of the process rank. So you have a continuous array with 4 elements. It means that the first element, so index 0 or 1, depending on your language, will be sent to rank 0, and then the second element will be sent to process 1, process 2, and process 3, and so on. So the elements are distributed in the order of the rank. This is what it means. And here in our example, we have an array of from a process 0, which is the root of the scatter, that will be distributed amongst the process. Of course, you can distribute multiple elements to the process dependent of what you specify in this function. So in this case of the scatter, and we will see that also with the gather, you can subdivide the arguments into 2 parts. 3 arguments. The 3 first only concern the scatter root. So this is the address of the data you want to scatter, as well as the number of elements to send to each process. And no, it's not the size of the array, it's the size of the number of elements that you want to send to each process, and then the data type. And on the other end of the communication, you have all the process that will receive the piece of data. And you specify the address of in memory that where you want to receive the data, the number of elements, which is supposed to be the same number as the one in the root, and the data type, which is expected also. You may think that it's completely stupid to specify 2 times the same information. This is what you will do most of the time. But the reason is that if you specify custom data type, we will not cover this subject today, but if you specify custom data type, for example, you create a struct of 3 float, which is a 3D point, Okay, you can send it as the custom data type on one end and receive it as 3 float on the other end. Because these data types are compatible in terms of structure, then you can have a different argument on the send and receive size, meaning on the root or in the other process. This is the reason why sometimes it may feel stupid to specify 2 times exactly the same value when you do a scatter or a gather, but there is a very good reason for people that do more advanced MPI. So, scatter example, we have data that we allocate and maybe the size of the group of process or the size of MPI world, and we will set the value to be I multiply by 100, I being the basically the process rank, as we loop over the rank, and fill this array with this data, and then we scatter it, and we say that, okay, from this array, we want to scatter 1 element per process, 1 element of integer type, data type to each process, and we will receive it in a variable that can be a scalar in this case because we receive only 1 element. Okay, and we specify that the scatter root, so the process that will scatter the data is the rank 0, and we use MPI convert for this scatter. And of course, as we allocated on the scatter root, we do free this data at the end. So what will this program do? Run on 4 processes is that you have your array with value 0, 100, 200, 300, so 100 times the rank. And each process, so process with rank 0, we receive value 0, process with rank 3, we receive 300, process with rank 2, 200, 100, and so forth. So we scatter the data. We start with an array of 4 elements, and each of the 4 processes will receive this 1 value from this array. The opposite of a scatter is a gather. So here we have a different piece of data located on each of the process, and we want to gather them in one array on the scatter root. So each of these processes have different piece of data, and they will gather them in the root process, and they will be ordered in the order of the rank. So of course, the value from process 0 will be the first one in the root, the array located on the root, as well as the process with rank 1 will be index 1 or 2, depending on your language, and so forth. This gather has exactly the same structure as the scatter function. So the idea behind it is similar, it's just in reverse. So you have the address of the piece of data that you want to send, the number of data that you will send, as well as the data type. And on the receiver side, you have, so in the root, you have the location in memory where you want to receive the data, the number of elements to receive per process, as well as the data type of these elements. So, example. This is exactly the reverse of what we have done with the scatter. So here we specify the value to gather as a scalar. Okay, it's value rank multiplied by 100. And on the gather root, we allocate a buffer that is big enough to contain all the value that will be received. So in this case, as we will send 1 element from each process, we need to have an array of at least size of int multiplied by size. And then we do the gather. So this is the send size. We send 1 value of MPI type, okay? And then we receive it in the buffer, 1 value per process. This is per process, and the type MPI type, and we gather that on MPI, the root of which is process 0, okay? And then you have some printing, and we free the buffer on the gather root. So the result of this, the execution of this program, is that you have, of course, all the values that in the memory of each individual process. So process 2 has value 200, process 0 has value 0, process 3 has value 300, and then when you go to the process 0, that is the root of the scatter, you get a nice ordered array with the value collected from each one of these processes. Okay, if we go back to sum of integer, this is what we were doing at the time is just having a send from all process with rank superior to 0, and then we have this loop here to receive the removed sums. And of course, it's not very efficient as basically we have word size -1 communication and when we increase the number of process, this may be very inefficient, and we can rewrite it using a gather. So all the removed sum will be gathered into an array, and then we loop on this array in order to do the final calculation. Okay, so if the process is rank 0, we allocate an array removed sums, which will be the size of the number of process. And after that, we do a gather, okay, for each individual sums computed on each process during the integer sum. We collect the value and then we store it in the removed sums array. In one step, we replace all this loop by just the gather, and then we do a loop on process with rank 0 to do the final sum. So this is a way to do this instead of having word size -1 step, you do this in log p step. Okay. What you can do also is a OR gather operation. So, oh, I don't know why this text is there. I make a mistake anyway. Okay. Anyway, what you can do is take piece of data and gather them to all the processes. So each of the processes will end up with the entire data set at the end of the OR gather. So we take a piece of data to all the from all the process, and then we collect them and they're present. So basically, this is a scatter followed by a broadcast. You can see that this way. And the OR gather has exactly the same signature as the scatter and gather, except that, of course, we don't have a root in this case, as all the process will receive exactly the same data and will end up with the same data in memory at the end. So you have the address of the value you want to send, the number of value, as well as the data type of this value, and then you have the place in memory where you want to receive them, the number of elements you will receive from each process, and the data type of this the value you want to send. So again, very simple example, when we specify the value on each rank, and then we do OR gather. So basically all the process will have a buffer filled with the value specified for each process. So the idea is that you have process that specify 0 specifies 0, 100, 300, 300, and all the process at the end of the OR gather operation end up with the entire set of value defined on each of the process. Okay, sorry. And then you have the all-to-all. It's a little bit more complicated to it allows for data distribution on all process, and it may look like a bulk transpose operation. So the idea is that if you have 3 processes, okay, and you have this array of rank 6, each of the destination array will receive 2 elements from each process in the order, okay, you take this array and you transpose it. So in this case, okay, the source 1020 will go to the first element in the destination, and then you go to the next rank, okay, and you take 2 elements and you fill the value with this. So 1121 will end up there. 1222, this is the 2 first value located on rank 2 of the source. And then if you go there, okay, on the destination for rank 1, then this is 2 pieces of data that will basically taken, so 3040, and then you go to rank 1, 3141, and then you go to rank 2, 3242, and so forth. Okay, so you can see that as a block transpose, okay, where these dimension transpose from the rank to the indexing in the destination array. Again, as this is all-to-all, we have no root, but you have exactly the same structure with the data you want to send, the location in memory of the data you want to send, the number of elements you want to send from each process, as well as the data type and the number of elements you will receive from each process, and the data type of these elements. So as a consequences, here we do MPI to all-to-all from an array with these fields with something dependent on the rank, as well as integer number that depends on the size. Basically, this array looks like this, okay? So if you go to process 0, you have 0, 100, 200, 400, and then continue on process 1, 400, 500, 600, 700, okay? If we do all-to-all communication of this data, okay? And we say that we want to receive 1 element from each process. This is what we say, okay? We send 1 element, we receive 1 element from each process. Then, of course, the process with rank 0 should receive 0, okay? And then the first value of process 1, 400, okay? And the first value of process 2, 800, and the first value of process 3, 1200, okay? So this is exactly what we see, okay? So the value of process 0 after the all-to-all is 0, 400, 800, 200. So this is basically the column, but it's been transposed, these rows, sorry, and it is transposed in terms of column. This is why I say it looks like a transpose operation. And you can see the same thing on process 1, okay? You have the value 100, 500, 900, 1300, okay? This is what we see on process 1. But you may say, okay, but what if I want to transfer the same number? I do not want to send the same number of elements from each process, because of course the problem with all these function, okay, MPI gather, is that you specify a number of elements that you want to send, but it's exactly the same for all the process. So if you have an irregular array, or at least you have not enough elements to send, what will happen? Of course, you can introduce a simple padding, okay, so that the size of your array is proportional to the size of the number of process, and just specify a random value there, or set the value to 0. But you can also use the vector variance of the scatter and gather operation. So this function that is vector variant will have a v at the end of the function name, and it allows for the message to be received to have different lengths and to be stored in arbitrary location. What it means is that if you want to scatter this data to rank 0, 1, and 2, okay, you can say that you want to send 3 elements, 2 elements, and 1 element, depending on the ranks, okay? And then you have to specify a displacement, so where to start for each process, and the number of elements that you want to send to each process. So this is done using an array of counts, so the number of elements to send to each process, and then displacement, where to find the data in the array that you are scattering. So I will show this as an example. So you have the MPI scatter, and then you have the variant version with a vector, which is scatter v. Okay, you add a v. You have the same with the gather. You have a gather v function. And the difference with the regular scatter is that, of course, you have the location in memory of the data you want to send, but then you have two supplementary array, which is the number of elements that you want to send to each process. So this array will be the size of the number of process in your communicator, and the value will be the number of elements you want to send. And then you have the displacement, where to find the data in the address to send to each process. You have the data type, of course, and then you have the number of elements to receive, as with regular scatter. And of course, you have the route, which process is supposed to send this data. Where is what is the location of the value that you want to send? This is the same with for the Fortran version. It didn't fit with the slides. And as an example, we have this, where we use rank 0 as the scatter route, okay? And we will create an irregular number of elements to send to each of the process. And basically, process with rank 0, we receive 1 element. Process with rank 1, we receive 2. With rank 2, we receive 3, and so on. So we use the triangular number. And so we defined a send buffer that will be this size. And then we set up two arrays, the displacements and number of elements, so the S count in the signature function that we just seen. That will be the size of the communicator. Okay, and then we fill this buffer with values, and we also set the displacement, where to find the values. And of course, with each rank, okay, so this is a loop on the ranks available in the communicator. So NLMs will be I plus 1, okay, which means that rank 0 will receive 1, rank 1 will receive 2, and so forth. And of course, you have to compute the displacement, so it will be 0 in the case of the first process, and then for rank 2 it will be 1, and then for rank for rank 1 it will be 1, and for rank 2 it will be 3. So you need to specify where to find the data that you want to scatter, and then you have this MPI scatter v function, okay. And we specify that the receive buffer must have the size rank plus 1, as we this is what we wish to do, okay? So you have the send buffer, the number of elements, and the displacement that is passed on the root size. And then for the receive buffers, it will receive the data in the memory that we have just allocated. And of course, this data we have size rank plus 1. And it's of type MPI integer. So as you can see, process 0 receive only one value, which is 100. Okay, this is exactly as is done here when we assign this. So of course, process 1 should receive 200 and 300, and so forth. If you go to process 2, 400, 500, 600, 700, 800, 900, 1000 for the process 3. And as you can see, each process receives different amounts of data. So only one element for the first process, and then 2 elements for the second one, and 3 elements for the process 2, and so forth. So this is a way to send irregular data using a scatter v function. And there is an equivalent, which is the gather v. So it's just the opposite. I will not do an example about that, but it's exactly the same principles. Sorry. So now we come to the point where we have to talk about the reduce operation. So data reduction is reducing a set of numbers into a smaller set of numbers. A sum is a very good example, or you find the minimum and maximum value for an array. So what you have is that you have a big chunk of data, And at the end, you end up with only one value if you do the sum of the elements of an array. The same apply for a min or max. You just get one value at the end of the operation on your data set. And the MPI reduce is done similarly to a broadcast, I would say. You have the address of the data you wish to reduce, and then the address where you want to get the result of this operation, and then you have the count and the data type. So the count will be the number of data elements, but the reduction will be done element-wise. What I mean by this is that this is the value. Okay, here we have only one value. So the value here will be summed with the value on rank 1, 2, and 3. But if you have a two-dimensional array, of course, it will be done element-wise. So you will be the first value that you will receive is the sum of all the elements at index 0 on each process. And then you will have a second element in your array that will be the sum of all the elements at index 1 in your array, and so forth. With index 2, you will get the sum of all the elements with index 2 on each process. Okay, so this is the count is exactly the number of the size of your send buffer. Okay, and you will receive exactly the same amounts of data there. And of course the type of data, and then you have this MPI op handle. Here, this is an integer representing for MPI an operation that it needs to perform. Okay, and then you have the route where to receive the final values. So the process that should receive all the values. And this MPI op can take multiple value. And for example, you have MPI min and max. Okay, or you have MPI sum, which is obviously a sum, or MPI prod, which is useful to compute a product. And of course, you have also a binary and logical operation. You can do MPI L AND or L OR for logical AND and OR operation, or you can do this bitwise with MPI B AND or B OR respectively. Okay, and you can create your custom operator type if you wish, but this will not be covered. This is way more advanced MPI. But if you need to, you can specify how to do a reduction, explain to MPI how to perform a custom reduction. Again, we can go back to our sum of integers. We have seen that we can improve with gather. But of course, we can remove all we have done with the gather, because in the gather, we still have a loop on the root process that is summing the value at the end. But you can rewrite this by just doing MPI reduce. So the idea is that all the value computed on each of the process will be reduced at the end on process 0 in the final sum variables. And of course, this is an operation with one elements per process. What's also possible is, like with the MPI gather all, you can also have an all reduce. It means that you can see that as a reduction operation first, and then a broadcast of the result of this reduction. So you have all your data present on all the processes, you do the reduction, and at the end, each process owns the value at the end of the reduction operation. Yes, it works with Python. This is the next part. So the MPI all reduce, in this case, the difference with the MPI reduce is that you don't have the root argument, because you don't need it, as the final result will be broadcasted to all the process. So it's exactly the same. You use you specify a location of the data you want to reduce, the location of where you want to get this value, as well as the data type, the number of value, and the operation you wish to perform. And as an example for the use of MPI all reduce and MPI reduce function, we will consider the computation of standard deviation, where basically we need to do the difference between the value and the mean of the value inside a population, and divide it by the size of the population, and then do the square root. So the idea is that first we need the mean. Okay, and if we scatter the value across the process, when we do this operation xi minus mu, the mean, we need that the mean will be available to all process. We need it. So what we can do is just compute the mean on each process and then do a reduction operation and reduce all operations so that the mean is available to all process, and then we can perform the operation of the xi minus mu. Okay, so it's exactly what we do. Okay, we compute the sum of all the elements. So this is values that we just randomly fill. We fill the array with random values, and then we perform the local sum of all the value we have created for each process. So this is the number of elements per rank. Okay, and after that we do a all reduce operation. Okay, with the local sum and the global sum that will be the result of this all reduce. And then on each process, we can compute the mean as the global sum divided by the number of elements per rank multiplied by the size, so the number of process. Okay, so we have the total number, the total size of our population by doing this. And because we have used the all reduce, all the process have access to the global sum, so the sum of the population. Okay, and then we can do our computation of the standard deviation, and in this case we can just use MPI reduce, because we don't want to have the result of the reduction at the end. On all process we just need to have it on a process with rank 0 for printing the result. So this is exactly what we do. We do the local square diff. Okay, this is the difference squared for each value of the population that we own for the process, minus the mean. Okay, and then we do this reduction operation, so the sum of all the local square diff, and then we do the printing at the end on a process with rank 0, as we have done this reduction operation only with process 0 as the root. So this is a mix of the usage of MPI or reduce. If you need the value of the reduction operator on each of the process, you use all reduce. If you only need the final value on one of the process, you use MPI reduce. Another thing that exists, which is a kind of a collective, because every process will wait for each other, is an MPI barrier. It synchronizes all the processes in a communicator, and each process will wait until all processes reach this point before proceeding further. This is a very few use case. It's used mainly for debugging, so that all processes reach the same point, and then you can check what is going on between 2 points in your code. Most of the time, a barrier is not needed, as when you do collective operation, all the process will synchronize on this point. Doing the operation, when they reach a collective operation, all the process have to be involved, and as a consequence, you have kind of a synchronization point, a natural synchronization point that arrives naturally from the use of collective communication. So MPI barrier are very, very few use case. Of course, with collective communication, what you can also do is doing non-blocking collective communication, it will not be covered, but yes, you can also, and then in this case, of course, this call to the scatter, broadcast, gather, and everything will not be blocking. But in our case, when we do all reduce, then all of this is waiting for the entire process to finish. Okay, this is the blocking operation, and this is the case for all the collective operation that we've discussed this afternoon. I've gone quite fast. So we reached a conclusion. So what we have covered today is three things: point-to-point communication, non-blocking communication, and collective communication. This is really a scratch of the surface of the possibilities offered by MPI. You can do a lot of different things. And of course, if I wish to discuss all the function, everything that is specified in the MPI standard, everything that is available, it takes me a week at least. As you can see, if you go to the documentation of OpenMPI, there is a lot of function available. This is quite huge, and it takes days to cover all possibilities of MPI. So basically what you can do also is, I speak a little bit about it, you can define your own data type, and it can be very useful if you have an array that and you want to describe how to send it. You can specify basically displacement and things like this and just send it as an object. You have persistent communication. When you do a loop and at every iteration of this loop, you can set up a persistent communication so that the communication can occur way more faster for each iteration if communication is needed at each iteration. Of course, you can also do one-sided communication, so it's kind of a remote memory access. So one process can have access to a small part of the memory of another one. And this is called one-sided communication, as the process from which the memory is read is not always aware of it. You can do parallel I/O. So you have function in MPI that is specified for, you see the MPI file, you get a lot of function that helps you to do parallel I/O. You have topologies. You can specify, arrange all your process in kind of a virtual topologies that will match your problem. So you can do a lot of things. And of course, we just scratched the surface. And if you, with practice, you have to go back to the documentation and the specification a lot to check what is available in MPI for your particular problem size, and how to do that the more efficient way, and if MPI provides something to do what you wish to do. So this concludes my part.
So hello again, everybody. So we are going to start with the presentation of how to use an MPI implementation in Python. This is just an overview of how to do some of the things that Oriane explained very detailed in Python. There are actually, well, some differences in the Python world, as you have here different kind of objects that you can communicate among. So in the very first slide, we see how do we go from serial to parallel with MPI4Py in case we have the MPI4Py module installed in our environment. So basically, if we have a Python code, we add all the procedure of initializing an MPI environment inside my code execution is just importing, as we do with other Python modules, it's just importing on the header the MPI4Py module with this way from MPI for Pi import MPI, and then we are inside that. Below that, we are inside an MPI environment. We have a communicator, ranks, processors, and we can do we can use all the kind of functions that Orion introduced before. So if in an environment where you have MPI for Pi available, if you go from just a hello world code and you initialize your MPI environment, then you run it this way. With MPI round, you specify the number of processors that you want, your Python interpreter, and then your Python code. And you will have your code below executed by 3 different processors. So that's just how you would initialize the code. But well, there are more details to take into account. As I said, with MPI for Pi, we initialize that way, and then you have to instantiate an MPI conword object from which we will do it this way, for instance, and then from that communicator object, you can obtain, with different methods of that object, you can obtain different information of your communicator. So that's a little bit of a difference between the plain C implementation and Python. But so these are the main things for the examples at the level that Orion showed before. These are the main variables that you would use to control the workflow of your MPI code. So instantiating the communicator, getting the rank of each processors and the number and the total number of processors. So in this Python implementation, there's no need to call some kind of MPI init and MPI finalize thing at the end. When you do the import of MPI for Pi, it already triggers the initialization, and then API finalize is already called when all the Python processes exit at the end of your code execution. And as I showed in the previous slide, running it plainly from the command line, it's very similar as you would do with a compiled C code. So MPI run -np, the number of processors, your Python interpreter, and then your code. Here, we are on Python, you don't need to compile. So as I said at the beginning, in the Python world, we have 2 different kind of what are called Python objects. The generic Python objects, so like Python lists and dictionaries, which are quite flexible in how to define them and what kind of elements they can have. They don't. Each element in a Python list must not be something with the same data type. So, and then we have what are called the Python buffer-like objects. In this case, these objects are defined in the Python standard as being an object allocated in contiguous memory, and in the case I have an array defined like that, each element of this array will have the same data type. So these are more equivalent to what would be defining a C array or a Fortran array. And these are the objects that are used mainly in numerical oriented Python extension like NumPy, pandas. So a NumPy array would be a Python buffer-like object. Pandas data frame the same. And the thing is that then the developer of the MPI for Pi implementation decided to work with these 2 different kind of objects on the MPI for Pi implementation, but because of the different nature of this kind of object, you cannot treat the communication functions the same way, especially when you have to split elements, like in a scatter V, for something as not so that you don't have to predefine in advance how much memory you are going to allocate, and you are going to mix different data types. You cannot do that in a trivial way. To scatter a Python list in which you have any kind of element in the different indexes of that list. So in this implementation, in this MPI for Pi implementation, you will find two different methods for the communicators. Always the one that are all lowercase, they are meant to be used for communicating generic Python objects, and the methods in which the communicator methods that start with uppercase letter, they are meant to be used to communicate memory buffers or Python buffer-like objects. And well, yeah, you have to take into account that communicating the communication of the generic objects, introducing a little bit of overhead, as you have to somehow do some special representation of this message before sending it and then restoring it on the receiving side. And then, of course, as I said, for objects are in nature buffer objects like NumPy arrays, pandas data frame. You must use the uppercase. They will actually work with the lowercase methods, but you must use the uppercase ones to avoid unnecessary performance loss. So a small example of how would like one of the first things that Orion showed in the morning. So we have now our hello world, but what we want to say each processor to identify itself. So instead of like in the very first slide that we just did the import of the import of MPI for Pi, and then we had the single hello world. Now we are defining the typical variables taken from the communicator that will allow me to tag and identify each process in my communicator. So we instantiate the communicator object, and then the getRank method will return for each processor executing this code its own rank, its own ID, and then the get size will give me the total amount of processors involved in this communicator. And then we can use this information that each processor got in the execution, is going to get in the execution of this code, and I can add more information to the print function. I can make then each processor to print a hello world and say, tell how many they are and tell which one it is. So if we run this small example, then you will get the hello world from process 0 of 3, 1 of 3, 2 of 3. And so the first, I already advanced something in the second slide regarding point-to-point communication, the first kind of communications that Orion introduced. As I said, well, for the blocking case, if we are going to communicate to send and receive a Python object, we do it with the lowercase send and receive method, and if it's a case of a NumPy array, we do it with the uppercase send and receive. And actually, for the way this is implemented for the case of for each case, the syntax is different because so here for sending a generic Python object. So this will be, for instance, like a Python dictionary. So each we specify in our code that we want to send, and then we actually we didn't remember that in the C code of doing a send and receive, you have to define in advance the array that it. So of course you have to define in advance the array you are going to send, allocate it in memory, assign values to it, but you have also to predefine in advance the array where you are going to receive the array or the variable where you're going to receive the values that it's going to be sent. So you have to predefine that in advance. Here you can define it at the moment. You for the Python object, you actually obtain the receiving message as an output of executing the receive method of the communicator, and you have to assign that. You assign that return from this lowercase receive function to your receiving object. For the buffers, as we will see in the example, it works more like in the C or Fortran case, in which you have to predefine in advance the message. So you have to pre-allocate in memory and define precisely its data type, also because NumPy arrays, they will have a specifically defined data type for each element of the array. So you have to predefine in advance and allocate in memory the object that you're going to send and the object you are going to receive. And then you, let's say, override in the receiving, you override in memory that you pre-allocated before. And as you see, well, the syntax here, it's closer to what you saw for the C case. So you have the element that it's sent and received. You have the count telling you the size of this array, and you have, well, the data type of each element of the array. And then, well, you have the tag, and also you have the source and the destination to be specified. The rank of the destination end and source, you have to specify it in the dest and earth keywords. And then, well, you have here below the equivalent case for a non-blocking communication. So how would you specify an I send and I receive for a generic Python object or for a NumPy array? And again, yeah, we have the to specify the syntax for the wait, for calling the wait method. It's slightly different. How would you do in each case? You will see, if you look through the internet for tutorials, you will see that for tutorials of MPI for Pi, you will see and you will find that even in the case, so in the case for the uppercase methods that you are sending buffer array, Python buffer objects, you will see that many would write the thing that I'm here surrounded with red, that instead of specifying the in a list the object that you are sending, the count and the data type, they are just specifying as a first argument of the send and receive the name of the variable in which you define your array or your single variable, because then in this implementation there will be automatic discovery data type, and then the count can be inferred also by the full size of the buffer. because remember that these things were predefined before in my Python code before calling these methods. But for clarity and to be more to keep to find the equivalence with what Oriane introduced before for C, I will keep in these small examples. I will keep showing the explicit definition of the list with the name of my variable, the count, and the data type. So how would it work? So here I have I'm showing a small example of how it works, the point-to-point communication of a fully generic Python object. So we have the initialization of MPI and the initialization of the rank and number of processors, and then for the processor, only for the one for the processor with rank 0, he will the processor will create this dictionary A. You see, well, as in Python, we can do, well, we have a fully generic dictionary with 3 elements, and then I tell to processor 0 to send to do a send of this A dictionary to the rest of processors. So from 1, so the 0 will send from 1 to the number of processors that I have in my communicator. And then for all the rest, they will be waiting for the message. And if I run this for 3 processors, and then we have the 0, only 0 creating and defining the dictionary and sending it to 2 and 3, and well, you would get an output as this when executing this code snippet. So as you can see, you can, well, you have the ability to send something completely generic as a dictionary. But then, as I mentioned, in the case that we are communicating something with a well-defined structure in memory, like a NumPy array, this will be closer to how we did it in how you saw in the C examples. So here we have also, well, the same initialization. We have to import NumPy also, and then in this case we are going to send an array of size 10. And so initialized this way, I already assigned values from 0 to, well, the size of my array -1. So the value of A created on processor 0 is, well, is this one that you see in the output that are received. But the difference is, as I mentioned, that you have to predefine. So you always predefine the object that you're going to send, as before we predefine the dictionary. But then on the receiving end, here we have to also pre-allocate in memory an array. We have to predefine it in memory, and then in this case we call it myA, and we assign zeros to it. So then you could try to print. To add a print before the receive to verify that you have it with zeros, and then after receiving the message, you get the output with the values that were received from processor 0. But you have to, yeah, as I said, to predefine in memory, to allocate in memory the space, well, predefine the variable and your array and allocate in memory the place for receiving your message, and then you specify, yeah, in the receive method, in the uppercase receive method, you specify where you are going to receive the message that you expect, and I will go back to the previous one so you see that here actually the receive doesn't have it doesn't have in the arguments I have to put to the receive the lowercase receive, it doesn't have the variable that you are going where you are going to receive it. You get that output returned by the method. So it won't work to put here a receive. So here, well, I introduced then the blocking send and receive, and here I'm showing you. I'm not sure if it's all on the screen, but if you are, well, we don't see the output below, but so this is the Python version of the of one of the examples that Orián showed in the morning. So how to implement the sum or the addition of the n first integers using the blocking point-to-point communications. I won't go in detail through explaining each line of the code. It's initializing, creating the intervals of each partial sum that each processor will take care of, and then so well each processor does the addition of an interval, and then it's communicated all the values to the processor of rank 0, which will do the final the final addition of what each processor did. You can look into detail. I will show you where you can find all these examples at the end. So for the case of collective communications, which was the topic of Orián during the afternoon, in which you have the scatter, gather, I'll gather, scatter V, gather V. We have the same difference between communicating generic Python objects and Python buffer-like objects, and well, we have the same. The developer decided for the same approach of having lowercase for generic Python object and uppercase for NumPy buffers. And so, but here also you have to make a decision for instance, what, how would you do a scatter of a fully generic thing like a Python dictionary or a Python list. So in this case, you have to, if you are going to be using collective communications of generic Python object, you cannot do it with any kind of list or any kind of dictionary. You will have to do the scatter. The scatter, for instance, will work if your dictionary or your list it has the same size as your total as the size of your communicator. Otherwise, it will crash. And then for the gather, it's the same thing. You will gather. Actually, you will get with the gather a list, the receiving object. It will be assigned to a list in which and you will gather a single element from each of the values that. So each sending object will be packed in a list of the size of your communicator. In principle, so the developer implemented it this way. You have to take a decision for something fully generic as a Python object, but clearly, if you're using MPI on Python for doing numerical computations, you will be using libraries as NumPy or treating with a Python buffer-like objects. So it's quite rare, I guess, that you will have to deal with those. And then, as we saw for the point-to-point communications, when you're treating with the buffer-like objects, the way to think your workflow or your code and to use these these methods, it's a way more close to how you will think about it in a C code. So you have to predefine your arrays, define the data type, and you give the count value as you saw in the examples that Orion gave. So I will go ahead then and show. So and then here I'm showing a code snippet of the example of how to do the sum of the first n integers, as you saw before for C, but for how would you do it with the collective communications with MPI for Pi on Python. So yeah, well, with using the collective communication, you simplify the code workflow. Sorry, I got that notification. And then, well, here I show just for illustrative purpose how it works. What I mentioned before, how it would work the scatter of a Python object. Like in this case, I have a Python list. So here I have some. Well, it's a very simple example. But as I mentioned, in the case of treating with a fully generic Python object, I define this list called full data, which has 3 elements. The third is still a list, but for full data is of size 3 as a list, as a Python list. And then, as I said, here to execute successfully the scatter of this fuel data defined on the processors of rank 0, it must be a Python object with size equal to the size of your communicator, so nproc that you get here before. Otherwise, it won't work. And then what it will do by default is it expect an object with size of the communicator, and it will just split. It will scatter that, providing one element of that list to each of the processors on the communicator. So 0 will get 23, 1 get AB, and 2 get the third element, which is a list with 2 values. And here, here I'm showing an example of how it will work, how it would work, the scatter of NumPy array. And as I mentioned on the slide, introducing the global communicator for Python, you here have the syntax is much more close to what we saw on the C case for the scatter MPI function. So you have to pre-allocate. So the object to be a scatter is defined by the processors with rank 0 full data. Is a NumPy array with 9 elements. So this code is, I have the assert of a number of processors equal to 3 because the code is hard coded to work only for 3 processors. But just to show a simple case for illustrative purpose. But so as you see here, the processor with rank 0 has the information to be scattered, and then you have to pre-allocate on 0. Well, on every other processor plus 0 that it's going to receive a piece of this scattered information. You have to predefine the my data array where we are going to receive the scatter values. And so, here we have a count of 3, and so each of the processor receive 3 elements from the scattered array. And if here below, I'm showing what would you get running this code in the terminal. So, in principle, that was it. As I mentioned at the beginning, the idea was to mainly emphasize what the differences are between the implementation in the Python implementation of MPI, how it differs because of the nature that in Python you have this different kind of objects that you don't have in C or Fortran, where you have to declare everything that you are going to work with. So for that, in the examples and in the slides, I emphasized the difference that you have if you treat with how you treat the communication of generic objects or buffer-like objects. But then the logic of developing an MPI parallel code and the way you have to think of organizing your workflow with the rank and using with the rank of the processors and using the different the different types of communication that you have among the process. That idea stays the same. So when you want to think how to parallelize one of your codes or part of your code, everything that Oriane introduced in the morning and the afternoon in detail, giving a deeper insight, stays true here. I just this module, this extra module at the end, is mainly showing how the special cases in Python differ from the C implementation. But then you can at the very end of the presentation you have the reference to the MPI for Pi documentation, and that's the best source to keep exploring how this MPI for Pi implementation works. But you have implemented basically all the methods, the MPI methods that were introduced in the previous session. You have all of them available on the MPI for Pi implementation. And so in this slide, I mentioned which in some of the clusters, which modules you have to load to get the MPI4Pi. It's already available on all the clusters, so you don't have to pip install, use Conda for using MPI4Pi. It's already available, provided as a module. And actually, before with the tool we use for doing the installation, this extension was for everything that it's before the 2018B release, just loading the Python module, you will have already that extension included. But then everything that is 2019A or higher, you will have to load a separate a part of loading the Python module. You will have to load a separate extra module in which you have the MPI4Pi extension installed. So in the case, by default, if you log in Lemaitre 3, you are already using the 2019B release. And then you have Python 3.7 available, but yeah, if you load it and you do from MPI4Pi import, it will fail, but that's just because you have to load also additionally the SciPy bundle that contains MPI4Pi, Pandas, NumPy, SciPy. So you don't need, on any of the SESI cluster, you don't have to do any kind of pip or Conda or on either. It's already available. And so I recommend you to attach to the latest, the 2019B. If you are on Lemaitre 3, on Dragon 2, you will see that by default you land on when you log in, the modules that you see correspond to the 2019B release, but you can do the module load releases 2019B to switch to and see what you have available in these new releases. And as I said, all the examples that I showed on the presentation that are, well, the name of each example is written below the code snippet when I show what you will get in the terminal when you execute it. They are all available, and actually there are even more. But so all I show, they are available here in this path in SESI, Frosh, Training, MPI, Python examples. Are all these files. So everything I showed is available there, and there are some extra examples showing all-to-all, and so showing non-blocking cases also. And in principle, so when we were doing this presentation on the traditional cases up to last year, so in everybody in a classroom, we were doing a hands-on session at the end, and we were given a small example. So I was focusing, well, in going through the presentation. I will look now if there are answers to take care of, but I propose you that you try to log in Lemaitre 3, load this, load the releases 2019B and these two modules. Well, you can test one of the examples I showed, and you can try to solve this exercise I proposed. Is well, basically, it's using just blocking standard blocking communications, make each processor to send a message containing its rank to the following one. So the processor 0 sends a message. What I propose in the example is to send 100 plus the value of my rank. So actually processor 0 will be sending 100 to P1, processor 1 will send 101 to processor 2, and so on. And then processor N will send 100 plus N to processor 0. So it's what's called a communication ring. You can, here you have a code snippet with what you have as to do. So you have to define somehow how to make each processor to point to the one on the left for sending and to the one on the right for receiving the message. And well, this is what you should get if you run the code for 5 processors. And well, at the end you have the references and how would you install MPI for Pi on different distributions. So you can, in this same folder, the example folder, you will find a file. So here, in that path, the message change to do is what is shown in the slide. So you can take that and try to implement the ring, and I will now look at if there are answers, or you can drop more answers. We stay available here.
Okay, thank you, Ariel. Thank you, Orion. We still have time for questions, so we will stop the video, but we will stay longer to answer questions in a Q&A. Do not forget the surveys. Thank you all for your participation.